Hello, everyone. Welcome. My name is Kambiz Ranavardi, a board member of ColumbiaDC and a graduate of School of Engineering and Applied Science. I would like to first thank our partners for this event, our affiliate, Columbia Alumni Association of New Jersey, and their members for being with us this evening. We're very privileged to have David Sulzer, Professor of Psychiatry, Neurology, and Pharmacology at Columbia University Irving Medical Center to talk to us about music, math, and mind, the physics and neuroscience of music, with a particular focus on how animals perceive and process music. This is, of course, the title of Professor Sulzer's new book with the Columbia University Press, the link of which is on our website, and we will also again share it when we share the recording of this session tomorrow. Please allow me to briefly introduce David, but I do encourage everyone to check our website for his full bio. David Sulzer is a professor in the departments of Psychiatry, Neurology, and Pharmacology at Columbia University Medical Center. His lab has made important contributions to the study of brain mechanisms involved in autism, Parkinson's disease, drug addiction, and learning and memory. He's also a composer and performer under the stage name Dave Sulzer, and has worked with many major figures in the classical jazz, and pop worlds, appearing on over 100 records. Some of his projects bridge music and neuroscience, including the Thai Elephant Orchestra and Orchestra of 14 Elephants in Northern Thailand, and the Brainwave Music Project, which uses EEGs of brain activity to create composition. Professor Sulzer, welcome.
Well, thank you very much, Kambiz. I appreciate the invitation and to particularly to speak to so many people from Columbia University, where I've essentially spent my entire adult life. I was a graduate student at Michigan State. We're getting some interesting feedback there. But I went to Columbia for graduate school, and I'm afraid I've been here ever since. Okay, so I thought it might be interesting to have a couple of questions to sort of focus our discussion tonight, and looking forward to your comments and questions and critiques at the end. And here are the two basic questions. Do other species, other animals that Kambiz was referring to, hear music like we do? And not to be coy, I will claim that in some cases, yeah, they certainly seem to. And I know that doesn't make sense yet, and I hope in a few minutes it will. And the second part will be an extension of this. And the question is, can other species play musical instruments? And of course, Kambiz already gave that away. You will hear elephants and a little bit of bonobos, and even birds play some musical instruments. So this might help us think about other species a little bit more like the way we think about our own. So let's start off with the math and the physics a little bit, but this is not going to be complicated. Now, I know that there are likely to be some engineers and physicists and math people on this call. Forgive me for making it a little simple for all of you, but this is so all the people in the arts who typically, as soon as you say numbers, go like, wait a minute, I can't understand it. You can understand this. This is only math that's requires grade school multiplication and division, nothing more than that. Yet you will, I hope over the next 10 minutes, really understand a great deal of how music is made in the air. So a little bit of background. So what we're going to try to build up to here is we hear some sounds as consonant and some sounds as noise or dissonance. And what does that mean? Are there physical reasons for this? And of course there are, or I wouldn't be going into this as a topic. So it's hard to think of waves in the air. You know, sound or air sound waves. It's essentially air pressure movement. It's kind of hard to think about that. So that's why we have this little drawing here from Lisa Haney, who's a very good cellist and bandoneon player, but also a very good artist. And what Lisa's drawing here is ocean waves, which are easy for us to understand because we see them. And just to introduce a couple of concepts here. So if we have these periodic waves, these waves going up and down, we'll see a movie in a bit, but you don't need a movie, you can understand this. We can start to measure ocean waves, and we measure them the same way we do sound waves in the air. And so there's the wavelength, and because they're repeating, you could measure from the top, where you could measure the distance between two tops or two bottoms or two middles. And this is typically when engineers do it. They like to measure it from the middle. And there are a couple of little cute things in here. One is the sailboat. So the sailboat, you can imagine you're at the beach, and the sailboat might be bobbing up and down with the waves, but mostly not moving towards the shore or away from the shore. This is a toy sailboat. And this gives you an idea of what's happening to the air molecules during the sound wave. So if I'm yelling at you or playing a clarinet at you, the air particles coming out of my clarinet are mostly not the ones that are hitting your ear. What you're doing instead is doing what's happening here. The airwaves in front of my voice or that clarinet are compressing and becoming higher pressure. Now, if it's water, if you compress them, it's hard to compress water. So it rises and it becomes higher. So that's the peak of the wave. Or it relaxes and that becomes the trough of the wave, right? So water waves are also being pushed together. The molecules are being pushed together and pulled apart. It's a little different with the gas like air because you actually can push. I just pushed a lot of air molecules together when I do this, right? And then you hear them essentially being pushed together. So when we talk about these waves, we think of them as periodic. That just means they're constant. You get a certain frequency of waves. And to give us some numbers on there, for what we can hear, the periodic waves that we hear start at about 20 hertz. So that means a hertz is once per second. So we can hear repeating waves of air or water, like this fellow listening to the fish, starting at about 20 peaks or troughs per second, up to, if we're teenagers, up to about 20,000 hertz. If you're my age, to about 15,000 hertz. Now, that sounds like a big drop off, but actually it's only about 3 or 4 notes on the piano. And in music, we only go up to, as the note that's being played by musical instruments, so the top note of a piccolo, the highest note in an orchestra, is roughly around 4,000 hertz. So the upper areas that we can still hear, we don't really use much in human music for an instrument to play. However, components of that sound do go up quite high. And this will also make sense to you quite shortly. So let's listen a little bit. I hope you can hear this. If you can't, maybe say something and we'll try. So this is just before the pandemic started. You know, us scientists probably were traveling too much to different meetings. This was the last meeting I went to, and it's in Porto, Portugal. So poor me, here I was at some neuroscience meeting in Portugal, and just taking a video with my iPhone over here. But you're hearing the sounds, right? And you're hearing the sounds of the waves. So what you're hearing is, and actually you can count how the frequency of the waves. So you can go, here, we'll just watch the swimmer. I'm pointing to 1, 1,000, 2, 1,000, there we go. So that was 2 waves, or rather 1 wave in about 2 seconds. So that would be about 0.5 of a hertz. But that's below what we're hearing. So what's all that shh and wavy sound that we're hearing? Well, that's something a little different. That's the waves pushing and pulling the air. And that's happening at a bunch of different frequencies. Now, let's look at that, and I hope this is going to work for you all. this is a free program called Audacity, and you can download it, and it's made by musicians, for musicians. Let's see if I can find it. How to be here. Okay, so this is, let's hear that recording of the waves again. So presumably you're hearing that, the sound of the waves. We could take a little bit here, and this is, you don't need to know how this works, but for the engineers, this is just a Fourier transform. And we're going to analyze it, and we're going to look at the spectra. And what do we see? Well, remember, we can hear down to below 50 hertz here, down to about 20 hertz. And we can hear up to about up here. And what we see here is virtually this whole area is covered. So that means there's sounds in many different frequencies. Essentially, this is white noise. It's the kind of sound that you get on the television or radio when you're not tuned into a channel. Now, let's think about how we can get what we think of as a musical sound. And this was a big problem also for people who were initially studying sound. People like Lord Raleigh and von Helmholtz and people like that. And one way they were able to start to understand what waves in the air could mean is by the invention of the siren. Now, the siren was originally invented as a sort of a musical toy that was also a scientific tool. First by a fellow in Scotland whose name skips my mind for a second, and then a fellow in France named de la Tour just improved it a little bit. So it's usually called de la Tour siren, but it's essentially the same kind of siren that, unless you're using a digital recorded siren in a police car or an ambulance or fire engine, it's still the same kind of siren. And the idea here, and you'll see why it was developed sort of by engineers to understand sound, is that you can turn a wheel, and now you can take a bellows and you can press out air. Now the air can only escape, of course, when a hole is traveling by, otherwise it's going to bounce back. So that means you push some high pressure air and it comes out here. Now, how fast does it come out? That depends on how fast you turn this crank. If you turned it, if there was one hole here and you turned it once a second, you'd be at 1 hertz. If he turns it 20 times a second, it would be 20 hertz, and we'd start to be able to hear it. Just like if the wave we just saw only happened once every 2 seconds, if it happened 20 times a second and it was kind of even, we'd hear it as a low pitch, a very low tone. It's sort of near the lowest note on a piano. So we're pushing the air out, and so we're getting high pressure air. And they showed that the more holes you put in here, which increases the number of air pulses per second, or the faster you turn it, the higher the pitch would be, the higher the note on the piano, for instance. Now, let's analyze this. Let's go back to our Audacity program, which I urge you all to download, and let's analyze this a bit. Let's look at a clarinet. Let's get rid of our ocean over here. And let's find a clarinet wherever I put the clarinet for you all. That's, is that a clarinet? Here's a clarinet. Okay, these are 2 notes in a clarinet. I hope you can hear them. Now, you remember on that ocean, we were getting waves all over the place. It filled everything. It filled the whole area that we can hear, from very low notes to very high notes. Now, I'm going to take this little area here, and we're going to analyze the spectrum again. And what do we see? Something very different, right? So the note that we heard, that first note, that I could tell you what pitch that is, because there's a big peak right here. And if I move the cursor over there, and you can see it says the peak is at 355 hertz. And that happens to be, if you're a piano player, the F above middle C. But that's, you only noticed one note, you only heard but these other notes are in here. And these notes turn out to be perfect multiples. So if we take 355 hertz over here as the note that the clarinet player thinks she's playing. She thinks she's playing the F above C, but also embedded in that are twice that. So you could see this next peak is happening at about, if you could see this, look where it says peak, about 700 hertz, okay? And then there's another one that's, again, so you take the 355, you add another 355, that's that peak, add another 355, that's that peak, you add another 135, that's that peak, and you see they decrease in power as they go down, but they're all there. So these notes are actually, this combination of notes put together in this way is what we think of, and in fact is the sound of a clarinet. And what it is are perfect number, whole number repeats or multiples. Just keep adding that number to itself and getting higher and higher frequencies. And those are called harmonics. Now, if you could see me, usually I would show this on a guitar or something. I'm in my lab right now, in the office in the lab, and I don't happen not to have a guitar, but I have a sung. This is an instrument that is played a lot up in northern Thailand, where the elephant orchestra is. And I bought this from one of the mahouts, one of the elephant trainers. It's got a Thai scale, and we'll actually come back to this Thai scale, because this is one of the most used scales in the world still. I hope you heard that. But the harmonic, if we just play the string, and I just touch, this is exactly half the length of the string, right here. This happens to be a third of the string. This happens to be 1/4 of the string. They're divided. So these harmonics are perfect divisions of the string. These harmonics that you're seeing on here are the resulting frequency, which is the reciprocal. Sorry about that, but what it means is if it's 1/2 the length of the string, turn that over, 1/2 becomes 2/1. And the harmonic in terms of frequency becomes 355, which is that fundamental frequency, times 2 becomes 700, etc. And we just build them up. So why is that happening in the string instrument? Because the string is vibrating 355 times a second, but there's also parts of the string which are divided by 2, and that one's going twice as fast, and a third as much, and that's going 3 times as fast. And all of those different pitches that we don't notice, because what we really notice is that this loud fundamental pitch, this is what we hear. The other ones are the added spice, like adding spice to a recipe, and come up with the, bolognese, if it were spice, or the sound of a sung that you just heard. Okay, still, I realize that this may be a little bit hard to accept. So there are experiments that you can do. This one's kind of cute. You can take a speaker. Now, if you play a low note in music and you watch the speaker cone, you can see it move back and forth. And what it's doing is it's pushing the air, just like the waves were pushing the air, and pulling on the air. So you start to set up these pressure points in the air, very similar to what you heard in the ocean, but here at a more even frequency. Now, if you do this in a hallway, those pressure will bounce back, and eventually they'll come up with a repeated pattern where they add to each other or they cancel each other. So this is sound, increased sound level, and this is anti-sound. I'm going to play you a sample of this shortly. And so, and you can sit in the hallway and walk through it, and depending upon the frequency or the pitch, how high or low the note is, you'll find that there are places where it's hard to hear because the air movement has kind of canceled itself out, or other places where it's very loud. So nice little experiment, and some people use this to compose music, mostly avant-garde composers, but one you may want to check out that I advocate is Phil Neblock. Phil has been doing this kind of music for about 50 years, and it sounds boring because he might be playing one note for an hour. And yes, that sounds boring, but it's actually not boring when you go there, because you find out that just moving a little bit very much changes the sound of the music. So this idea that you could divide the string up into even parts, into 1/2 or 1/3 or 1/4, and derive the scale goes back a long time. Now, probably came from, it's very old, but the understanding of it probably came from India, but in Europe, it's usually associated with Pythagoras, who lived mostly in present-day Italy. His school was in Calabria in southern Italy. At the time, it was, the Greek culture, people spoke Greek. And this is a drawing Lisa has done on an instrument that he is supposed to have used, called a monochord, meaning just a single string. And by pinching the note or using another bridge over here and stopping the string so that it's only half as long or a third as long or a fourth as long, he could derive the whole musical do, re, mi, fa, sol, and the do scale. And you can go on the math of that, and it's very beautiful, and it's been the Pythagoreans and people for thousands of years since have been finding metaphysical and spiritual sustenance from this, with the idea that, look, we can make in tune notes from this that resonate with each other. The universe must make sense. And I realize that sounds like a big exaggeration, but this is where, this is where quantum physics came from, if you could believe that. Einstein said de Broglie thought of quantum jumps in the electron because of his familiarity with organ pipes, which do this. And Johannes Kepler discovering the elliptical, sorry, neurologist, elliptical movements of the planets, did it so that the planets would sing in tune. And Newton came up with the term spectra and the ideas that the different colors in the prism must stop and start at particular wavelengths. In fact, originally he said that the colors in the prism correspond to particular notes in the scale. So it actually has been very important through the millennia. Pythagoras, by the way, left no writings himself, and so there are a lot of great stories about him if you like to do with it. But one of the stories, which will come up very shortly, is he thought, and his followers thought, the string should just be divided into perfect parts, 1/2, 1/3, 1/4. And one of his people found out, well, you can't do that with the square root of 2. It's related to the Pythagorean theorem, but it doesn't matter. You can't find a simple number that will divide by the square root of 2. And supposedly they were so shocked, they drowned this person because they didn't want anybody to know about it. But our music is partly based on the square root of 2. Again, we'll get into that very shortly. So this idea of having a few notes on basic divisions of a length, it doesn't just happen with strings, it also happens with instruments like flutes. And this is a reconstruction of the oldest instrument that's been found. It's from about 35,000 years ago. It's from a cave in southern Germany, which is also the cave where the oldest surviving figurative art has been found. And Wolfheim here is an instrument maker that is trying to recreate these ancient instruments. And so here's one that his daughter is playing. It was constructed of a whooper swan bird bone. These caves have musical instruments that are so old that one of them is made from a mammoth tusk. So it was made from when there were still mammoths in Germany. And they play a scale, which is essentially the pentatonic, it's not exactly, but very close to the pentatonic scale we use now. That's used in the Thai scale that you heard, tuned a little bit differently, but still at the same scale. It's used in, I've counted pop songs on the radio, one day when I was counting them, about 70% of the top 40 sorts of pop songs in the radio that I was hearing last year are using pentatonic scales. So very widespread, virtually all popular music from China, from Thailand, from Korea, from Ethiopia uses this scale, but we were using about 35,000 years ago, which is already telling us, I think, something. Now let's think about what happens when you divide the string or the flute into these sounds. And what happens, so this particular wave is 440 times a second, 440 hertz. And the reason I choose that one is because it's not only the A string on the violin, and you know, in an orchestra, the violin player, when they tune, will play that string and everybody tunes to it. But the oboe gets up at the beginning and holds the note and the whole orchestra tunes. And in the Americas, that's 440 hertz. So it's a little bit different in Europe, but close. And so this F2 is taking that 440 and multiplying it by 2, just adding another 440. And this one, you add another 440, so it's 3 times the frequency, and so on. Now let's go back to Audacity, and we're going to hear what that sounds like. First, we will get rid of our clarinet over here. Goodbye, clarinet. And here's 440 hertz. So we're going to start. Let's start. I'm going to mute these guys and bring them in one by one. So let's start here. Here, you should hear the 440 hertz. This is the note. Okay, that's the note that the oboe plays. Now we're going to add 880 hertz, and you're going to hear that it sounds quite consonant. For the musicians, this is 1 octave. Okay, now 3 times the frequency. So that's 440 plus 440 plus 440 equals 1320. And for the musicians, this is 1 octave and a fifth. And here the 4th, which is the next octave higher. For the musicians, this next one will be a major 3rd. Okay, a boring sound, but very consonant. Now, let's hear if we take that, instead of using this one, let's use the one that's a square root of 2. So this is 440 hertz. Now let's add another note, which is that note that the Pythagoreans killed for, the square root of 2, and hear what that sounds like. Okay, so that's a little more disturbing. And I hope you could see this. This is a internet piano thing. Instead of playing the piano, I thought it might be nice to hear it. So that's this note. This is an A. And this is that square root of 2. To musicians, they'll call this a tritone. And that's a little disturbing. And we wanted to, most classical music and most jazz music is written so these 2 notes will hit a consonance, and the consonants are those perfect multiple intervals we just heard, right? So you go, or you can go, let's see if I could do this. Okay, so if you heard that virtually from Mozart and Bach and George Gershwin and on and on, Stephen Foster and Duke Ellington and on, this music that we have grown up with is essentially based on trying to take that square root of 2 and move it to a consonant, which comes from a whole number multiple. Okay, so this is something that's essentially very basic. Let's go back over here. So you could see that if we add these together, you get a periodic wave. It's a complicated wave, but it's exactly the same each time. And it's got this little dip in here. That's where the troughs make it quieter, and here where they make it louder. But what if you take those 2 dissonant notes that I just showed you, the so-called tritone, they used to call it the devil's interval, and add them together, where you could see it's much less reproducible. It actually is kind of reproducible, but it doesn't have that nice recurrent pattern, and it sounds dissonant to us. Now, what happens if you have a couple of notes which are a little bit out of tune? What happens is sometimes the notes reinforce. So the peak here adds to the peak there, and you get bigger peaks. And other times they're a little bit out of phase and they cancel. So you can see, again, there's such a thing as sound and anti-sound. So when you have sound canceling headphones, they work this way. And I think this might be the last, or nearly the last Audacity program I'm going to show you. Let me get rid of my internet, my email. Why do I see email on here? Let's try to get the right. Here we go. Okay, so here's one note at 300 hertz. So I'm going to trust you hear that. Now here's 301 hertz, which is not going to sound different to you. If it does sound different, you have incredibly good hearing. Okay, so they sound the same. But you see, this is 300 times a second. This is 301 times a second. Now let's listen to them together. So I hope you heard how they go, wow, wow, wow. And how fast is that? I could tell you, because 301 times a second minus 300 times a second is once per second. So they're 1 hertz difference. And you heard a beat at 1 times a second, 1 time a second. If it was 302 hertz plus 300 hertz, you'd hear 2 beats a second, essentially. Every musician uses this beating phenomena to tune their instruments, although most of them, frankly, don't understand why it works. Now, let's add more and more of out-of-tune notes, and you start to get stuff that, just a little bit out. But instead of getting that nice, reproducible kind of wave that keeps repeating, as you saw before, you start to get something which is very non-recurrent, and this now really starts to become noise. So there is, I hope, leading you up to this, I've kind of said what I want to say about it, but now you can hear that there are physical reasons that some things sound consonant and other things sound noisy. By the way, this is just fun. There are colors of noise. You've heard of white noise, which it sounds like, like. And there's pink noise and brown noise. Just play a little bit that we generated on Audacity for you. And this, yes, we'll save it. Thank you very much. So let's first listen to the sound of white noise. This is where every frequency is represented. Okay, you're familiar with that from the snow on your TV or radio. Here's pink noise, which tends to be more in the lower frequencies. And we won't talk about it right now, but that's kind of how your ear works. So this is a little more relaxing. Some people use it as a sleeping aid. It sounds like white noise, but a little less, bit less of the fingernails on the chalkboard. This is brown noise, which is still more in the lower pitches. But all this is mathematically defined. You can recreate it, and it will sound just like this. That's kind of sounding like a peaceful seashore. Okay, so we've been talking about now, if you've been following all this, I know it's a lot of information, but like I said, all you need is multiplication and division to follow everything I've said, and still the same for everything I'm going to say. So how does the brain perceive this? Now, this work comes from Mark Tramo, who is a neurologist now at UCLA. And what he's doing is, now we're starting to talk about if other animals hear the way that we do. Here he's recording from the auditory nerve of a cat. The cat is under anesthesia. And he's playing these notes, which the perfect fifth is, this happens to be A440. And this note is essentially the 3 times the frequency of this note, and then brought down by an octave. But anyway, very consonant. And just like you saw this periodic wave in the air, you can see a periodic wave here in the cat's auditory nerve, carrying the sound from the ear up to the brain. So you could see this very nicely. Now let's take the devil's interval, that square root of 2 interval, and you can see it's already becoming much more complex, and that you don't get these nice, clearly reproducible peaks. It becomes much more complex. And if you get much more dissonant here, it becomes still more complex. So the way that the nerves are carrying the sound from the ear to the brain are very similar to the waves in your computer or your CD player or your record, the grooves on the record player, or an instrument or speaker moving the periodically moving the air to higher and lower air pressure. So if you took this and put it into a speaker, you would essentially hear whatever the sound or the music the cat was hearing played back. So at least up to this point, you could see that what we hear in the air and what we have in the ear, even though this is actually electrical activity, it's no longer the air moving. It's very, very similar. And so obviously I've skipped a lot of steps to go from the air into the brain. I'm not trying to push my book or anything, but if you want to understand those steps, they are in the book, and I hope explained in a clear way. Now, what happens when we finally get into the brain after that auditory nerve? So to understand that, a lot of the understanding is happening in the outer part of the brain known as the cortex. And here's a human cortex. Now, this is all work that comes from Wilder Penfield. Used to be at Columbia, had a fight with the department, moved to Montreal, where he established the Montreal Neurological Institute. And he's a very good writer. And listening to his, or reading his books or his articles, or like reading a novel. In fact, when he retired, he became a novelist. So he was doing brain surgery for people with epilepsy. And when he was doing this, he would take an electrode and the person would be awake. Now, around the skull would be anesthetized, and there'd be a little hole in the skull. And he would put in the electrode. And if he touched over here, the patient would feel something, depending upon where he was along this area that here he's calling the somatic cortex. And over here, if he was touching with the electrode and giving a little bit of electrical current, he could activate the movement of the muscles. And actually the sound area happens to be right in here. It's kind of curved over, so you don't see it exactly. And so you may have seen this drawing before. This is Penfield's drawing. It's called the homunculus. And so it's those two areas I showed you at first, and you could see parts of that there's a lot of your cortex, which is devoted to your hand, less, say, to the jaw, a little bit here to the neck. Has to do with, in fact, why we can do so many things with our hands, and the sensory area. And you get, for instance, a large part of your sensory area is devoted to the face. So these kinds of surgery are still done now. And they're, of course, epilepsy is very common. If there are probably many people listening to this, listening to me right now, who have epilepsy or did have epilepsy. Most typically it's treated by drugs these days, but for some people, this sort of surgery is still done. It's essentially the same surgery that Penfield was doing with the technical advance that rather than using a single electrode, now we'll use multi-electrodes. So each of these little red dots, this is on a person, a drawing on a person getting the surgery, and this is where they were. And a little bit of, there would be a small little ablation of the area where the seizure starts, and typically these can be very successful. The people no longer have the seizures. So while this was happening, a professor at Columbia named Nima Mescarani made a recording, and the recording is very simple. It's just, and what eyes they were, okay? and they play that for the patient. Now, when they play this, and this is breaking it down to the sounds. So that's an n, w, r, z, o, a, breaking this up and what eyes they were into parts. And these are the frequencies. It's called a sonogram. And so you get those frequencies, same frequencies we were talking about with musical notes. In fact, you can see the harmonics here. You see each of these stripes? Those are perfect multiples of each pitch that the speaker is saying. And here is the resulting brain activity. And there are different electrodes, and you can see that different electrodes around here are being activated depending upon what particular sound that that person is hearing. And here you can try to map out where along here each of these phonemes, vowels and consonants, are activating which parts of the cortex over here. Now, here is another paper, also from Nima Mescarani's lab, and very similar. You take some sounds like frictive sounds, which are F and S and so on, or plosive sounds like P and B and K, and you try to figure out which parts are responding in the cortex to the sounds. Now, where did this come from? Is this another patient? No, this is a ferret. This is a ferret who is also responding with the ferret's auditory cortex to human spoken sentences. So you go back to the claim I was making at the beginning that animals do hear like we do. This is part of the reason I think this happens, is from these experiments. Now, obviously the ferrets did not develop their brain to understand human speech, and yet this is retained. So at this point, I want to finish this first part. Do other animals hear like we do? Well, the frequency ranges can be very different. If you remember, we hear from about 20 times a second up to 20,000 times. Elephants hear about an octave lower, that means 10 hertz to 10,000 hertz on both ends. Bats can hear up to 200,000 hertz. Whales, some kinds of whales can hear much lower and much higher. They can hear sort of like from below elephants to above, in the range of the bats. So the frequency ranges can be very different, but the harmonies are built from physical properties. And so for the understanding of what sounds consonant and what sounds dissonant, they do look to be retained, at least for animals with an auditory cortex. And are they also retained for other animals who hear without an auditory cortex? As you could tell, I suspect they are, but we know less about that. So for instance, if you're a grasshopper, you don't have an auditory cortex, but and there many animals here, and this goes for many insects and so on too. Do they hear the same way we do? Moths can, quote, hear by the vibrations in a twig. Do they hear consonance and dissonance like we do? I suspect to some extent they kind of do. At least the dissonance would be frequencies that aren't not perfect multiples. Question number 2, because I know I'm taking a lot of time, but this is a lot of information. I hope you guys are enjoying it. Can other species play musical instruments? So we started this with Ofer Chernovsky, who is a professor in Hunter College in New York, and is one of the specialists in, well, maybe the top specialist in how birds learn to sing. This is a zebra finch, and a lot of the work is done with zebra finches, who are songbirds for various reasons, including that they're easy to raise. So Ofer figured out how to make a little lever here. And when the zebra finch pushes the lever, it hears back a sound. In Ofer's case, it was the sound of his father's own song, so that the bird can learn to imitate his father's song. And you'll see this now in the video, and you'll notice his tail feathers ruffling. That's a sign of interest and excitement. Hearing his dad, and see those tail feathers over there. So with some friends, I decided to move this further and see, would they play other birds' songs? And they will. They said, will they play human music? And yes, they will. So I had 4 of these zebra finches in the house for a while, took those same kind of levers, and then I'd leave and go up to the lab for the day, come back and see what they played. here's one of the pieces they're playing. So they're singing along with themselves while they are playing. They're triggering these instruments. Here they're triggering trombones and trumpets. They like some instruments much more than others. Some they'll play once and they won't play again. Others, literally, sometimes in the day, they'll play hundreds of times an hour. So, in the interest of time, as beautiful as I find that, we won't listen to the whole thing, but you are hearing the birds making calls and at the same time playing musical instruments. They like gamelan orchestras, so here they are sampling. Each of these samples is a couple of seconds long, and they are deciding where, they are triggering and deciding where and when to play the music. And you also hear them sort of singing along with it. Okay, and if you'd like to hear more of this, these are on my website. You can download them. Okay, so we'd like to see if wild songbirds, these are cage songbirds, domesticated, if you will wild birds, especially ones like mockingbirds or nightingales that are sing a lot of different songs, would they also play musical instruments in the wild if they were designed for them? Ofer thinks confidently that they would. We have not done this. If somebody's interested in working with us on that, please be in touch with me. If I didn't live in New York City, I would do this myself. And there are lots of questions you can do, like how their taste changed and so on. We're going to listen just a little bit to a bonobo. This is Sue Savage Roomba. Some of you may know about her. She is the world expert on teaching bonobos to communicate in a human way. They can communicate with us via sign language quite well. We don't understand their communication at all. Here is Kanzi playing on a synthesizer along with the musician Peter Gabriel, who's playing synthesizer. So Peter's, you can't see him quite back here, but he's playing drones on a synth, and Kanzi is jamming along on the keyboard. And this becomes pretty interesting because the notes that Kanzi chooses are ones that sound very harmonic and consonant to us. There's no reason that he has to do that. He does it, and he particularly likes playing octaves. So finally, we'll talk about the elephants that you've been hearing about. Now, you may have heard of the painting elephants. These are the same elephants. They're at the Thai Elephant Conservation Center in Lampang, near Chiang Mai. The project originally was done with Richard Lair, an American who's the world's expert in Southeast Asian elephant conservation and behavior. He's lived in Thailand for over 50 years. And Komar and Melamede, painters here in New York. This is a bit of where the conservation center is. So the elephants live in these forests at night. They come in during the day. They are domesticated elephants. Elephants have been domesticated in Southeast Asia for 5,000 years. This center is the first conservation center for the elephant. There's about 100 elephants now living there. It's owned by the Thai government. Now there are about 100 other centers. This is the only one that's actually owned and run by the government. We recorded 3 CDs of the Elephant Orchestra between 2000 and 2006. We're no longer have the orchestra, but the elephants still play instruments once or twice a day, which is something they like to do. It's social, and you don't have to force an elephant to play an instrument. They enjoy they enjoy doing this. So here's some of the instruments. We built over 20 instruments. This was the most successful of the instruments. It's based on a traditional Thai instrument called a renat, which is like a marimba. I'm just showing this to you because the way I made this is using the same rules that I showed you before. So for instance, the octave is a bar, which is twice essentially the length. And you can come up with that same pentatonic scale that our species was using 35,000 years ago. This is how you build it. I built it at a metal shop in Lampang. This is how it looks and how the elephant plays it. Elephants learn this in just a couple of minutes. It's very ergonomic. And if it's in tune, they enjoy playing it. So here's one playing a bass drum. Lee Oscar, who makes harmonicas, was very kind and made us special harmonicas for elephants to play in the Thai scale. As you can see, they play them by holding them in their trunk. And here are other instruments that I made. They all play in the Thai scale. Now, why did I put it in Thai pentatonic scale? There's several reasons, but the most important is because the important audience for the elephants are the people that live there. And by putting it in the Thai scale and various other things that we've done, including using temple drums, it does resemble the music of the Buddhist temples and the animist temples in northern Thailand. These are called angaloons, tuned rattles. To the same way that Americans know the auto harp as a grade school instrument, everyone in Thailand knows this instrument. And here's a little bit of a video. There's lots of this music, but here's a video of the orchestra playing. Now, these are a couple of women that live in the village here playing rain sticks. That's the only human sounds you're going to hear here. We built these and we couldn't get the elephants to learn them, but as you'll see, so that's why we have humans playing them. The rest, as you'll see, are all being played by elephants. So altogether, about 21 elephants have learned to play instruments. This is where I'm going to leave this, a little bit of conservation. If you'd like to read this article, you have to download it because I doubt any of you are subscribed to the Journal of the Elephant Managers Association. But Richard Lair wrote in 2019. So there were over 100,000 domesticated elephants in Thailand 120 years ago. The population now is only about 3,700. There's also about 3,000 still in the wild. 95% of them are owned. They're in private hands, not in public hands. Since logging was banned in 1989, which is another early conservation story. In fact, it's an early story of climate change. Tourism is their only work. And so now there are about 100 private camps, plus that one government-owned camp that you just saw. So main health concern continues to be overwork of the elephants. The ones at the Conservation Center well treated, they work for about 4 hours a day. Now, the tourism is mostly funded by Chinese visitors. There aren't that many Western visitors there. As was seen in the SARS epidemic, this causes a big problem because when the tourists disappear, like they just have, this becomes a major problem. Elephants have major veterinary problems. They eat 400 pounds a day, and there are a lot of issues, and we're going to have to be much smarter in planning for the conservation. And as the population dwindles, as you can imagine, there's going to be problems with inbreeding and genetic issues, and we're just going to have to become much smarter at the preservation of the species. So, question 2, I'm actually done. Will other species play musical instruments? Yes, as you saw, songbirds will do it, bonobos, elephants, we're just scratching the surface. Wild birds is a big question we have. We'd love to have some people that live out in the country who have wild birds to maybe work with us on this. The instruments must be ergonomic. They must make attractive sounds to the species. That's important because when people have made bad elephant marimbas, which happened at a zoo I won't name, the elephants don't want to play it. They want to play things that sound good. So this, of course, could also be done with dolphins. With Diana Reese, also a hunter, has been working on ways that dolphins can trigger sound. And of course, we think they could trigger music too. All right, so that's my talk. I hope you guys enjoyed it, and I'm going to stop sharing, and I hope that you all have some questions, comments, and so on. Thank you very much.
Great, thank you so much. My name is Miyako Yerrick, and I'm the administrator for the Columbia-DC Club. I'm just trying to get my video to start, but we can go ahead and start with the Q&A. We have a lot of thoughts coming in. So I'm going to kind of go back to the beginning of your talk and work my way down. For everybody listening, we are recording and we'll share the link. I know some people had to drop off. And please post your questions into the Q&A, not into the chat. It just helps me kind of get through them.
Were you able to hear the demonstrations, like the Audacity programs and the piano and so on?
Yes. Yes.
Good. Wow, that's a relief. Okay, thank you.
I think there was somebody who was hoping you could be bigger when you were playing the stringed instrument, but we could hear everything.
I don't know how to make myself bigger.
All right. Okay, so here we go. There are some questions. The first one that came in is,
oh, you've got a cello. Okay, can you do some demonstration if we ask you?
I cannot. My husband plays the cello, and I don't know if it's in tune right now.
You can send it back to the factory and get it tuned.
Okay, so let's see. Our first question here is, are there any frequencies or harmonics that are more prevalent in nature?
Yeah. So these perfect multiples, the 2s, 3s, 4s, 5s, are very are extremely common in nature. And you actually saw that on one of the sonograms I showed you. That was a human speaking. But if you look at a bird sonogram, and if you really want to get into this, I urge you to go to the Cornell Lab of Ornithology website. And you can look at and make your own sonograms. They have a free program called Raven that you can download, and then you can analyze bird songs. And you will see that that kind of harmonic consonant stack is happening within the bird songs as well. So in a way, it's a property of physics. It's a property of vocal cords, or in the case of birds, we call it a syrinx. They have sort of a double vocal cord. So it happens all the time. So those would be the most common harmonics in nature.
And on the birds, somebody asked what instruments or what sounds do the birds not like to trigger?
So I put in a punk Delta band from Memphis called the Oblivions that I enjoy. It's sort of a, 1980s abrasive jump up and down, distorted guitar. I don't, if Greg or the other Oblivions would be listening, I don't think they'd be insulted by this. I think they're proud of what they do. But the Birds played that once and never wanted to play it again. They also did this, so it's not just rock and roll musicians. I gave them the sound of a canary, and canaries, for some reason, can terrify zebra finches. And they play, you know, canaries sing beautifully, right? We raised them to be great singers. And they played that once, and they started squawking and getting very scared and so on, and they never played that one again. So that would be two examples. I have the feeling that at least when they begin to do this, they like the sounds of human instruments that sound like them. And they're called, you know, canaries have very mellifluous call. Zebra finches, you heard them a little bit, they kind of sound like, and so they like trumpets, and you know, they like, at least at the beginning, those are the kind of sounds I think that appeal to them. So I have the feeling that for many species, including ours, we kind of like music that's around the frequencies and maybe the timing of our own communication and what we listen to. There's a lot of stuff going around us all the time that we just simply don't focus on. And the stuff we do focus on is kind of in the vicinity of where we have our speech communication. That's where we tend to put our music. The male voice is around 200 or 300 hertz. It's a little bit under, you know, it's about two notes under middle C. And female above an octave or a fifth above that. And that's where we tend to put our melodies. So I suspect that it's very similar for other species as well. You know, you tune in where it's important to you, and that's sort of maybe for art as well as for communication.
Okay, so we have a bunch of questions coming in. Thank you to everyone putting them in the Q&A. If you did post a question in the chat, if you could just repost it into the Q&A for me, it's a little easier for me to catch. Okay, so we had somebody ask early on if science could eventually, if it hasn't already, produce a combination of sounds and synthesize something that's more pleasing to the human brain than what is composed by humans.
Yeah, I'm very skeptical of that. I'm very skeptical of AI and deep learning at coming up with like absolutely brilliant new findings. I still think human trial and error and intuition are pretty valuable. So I can't say never, but you know, I've actually satirized that before. If somebody wants to hear the most wanted and least wanted music, we essentially are doing that. We're taking polls of what people like and what they don't like and putting them together, and it should be music that everybody loves and everybody hates. And in fact, it doesn't work like that at all. So I'm very skeptical that, in fact, I kind of don't believe that we're going to come up with Miles Davis or Maurice Ravel or Joni Mitchell or whatever by doing AI. Having said that, I do have a project where we're kind of trying to do that. So just because I don't believe it doesn't mean that it's not worth fooling around with. And just like we were saying with the spectra or quantum physics or the elliptical orbits of the planets, many of our technological ideas actually came from music, initially from music. So perhaps something out of here, something that we can't imagine. I hope it's good. I hope it's good for people and other species, may come out of this kind of work anyway.
So we're getting quite a few questions about the elephants.
Good.
It's pretty common. So we had Terry ask, what kind of work do the elephants do at the government preserve in Thailand? You mentioned they work 4 hours a day. And then Carol also asked if the elephants get cues from their handlers telling them when or where to hit the instrument, or if they're actually doing it themselves.
Yeah, so first question, their work at almost all these centers is tourism. So the elephants do shows. So these elephants will do 2 or 3 shows a day. The shows are about half an hour long. And they come out and they march around and they do some touristy tricks. But the touristy tricks, so the ones that, if you've seen them in circuses, like elephants don't like to be on their hind legs, for instance. They don't. There's certain things they are good for them. Other ones are less good. So at the center, they're very careful to give ones which are healthy, safe, enjoyable for the elephants. But they'll do things like move logs. You know, you could see how most of these elephants were logging elephants before logging was outlawed. So you could see them carry logs and arrange a pyramid. Like they could do things that our domesticated animals could never do. The other work they do sometimes is you can go there and spend some time there and take the elephant Mahout training program. So it's kind of work for the elephants, but essentially you learn how to ride them, how to give commands, things like that. And so essentially that's work for the elephants too. So that's pretty much the work that the elephants do at the conservation center. There are a couple of conservation centers where they don't do any work. You just pay to watch them, nothing else. And in a way that at least should be the best. You know, is it actually the best is another question, but it ought to be. So, you know, for people that can do that, I'd urge you to do that. The second question actually relates to the first, which is how much are the Mahouts telling them what to do? And that's a hard one, and I genuinely mean this. It's a hard one to answer. So in the video that you just saw of the elephants playing, each elephant has a Mahout next to it. The Mahout may be saying, okay, time to play, but that's because I was there. You might have seen the bald guy in the middle going like, okay. So some of the elephants actually learn when I do that, that means start and stop. But most of them don't learn that. And so the Mahout is mostly saying start, stop. The Mahouts are not telling them what rhythms to play in or what notes to hit. Once in a while, they may go, and I actually try to get them to stop doing that, but the Mahouts want to be involved too, of course. And so the elephant may be playing a lot in the low notes, and he says, no, go over to the high notes. Now, some of the elephants will not stop playing, and you cannot get, and I know this sounds nuts, but believe me, it's true. You cannot, these animals can weigh up to 10,000 pounds. And an elephant trunk is, if you took the strongest men in the world, it's nothing like an elephant trunk. You cannot imagine how strong. You cannot get an elephant to stop playing or whatever if it doesn't want to. So one of the, we could go back into it, but one of the shots in the video, the Mahout is actually saying to this particular Maycot, and he's going, Maycot, stop. And she's going, bang. Anyway, now the first time Maycot played the one of those instruments, it was the one with the big aluminum thing that was wrapped over kind of a tree trunk. We call it a thunder sheet. The first time she played it, she yelled and was scared. Then she picked it up and kept playing it. So she enjoys playing. It's a big loud sound, and she really enjoys playing it. And getting her to stop can be hard. Sometimes the Mahout is trying to wrestle the beater out of Maycot's trunk. So that's why it's hard to say. I mean, Richard's instructions and my instructions are start and stop. Now, having said that, also to make another layer of complexity, the instruments in the orchestra, of course, either I personally built them or they were built by people working there, and they all fit a scale. So that means they're already circumscribed in what they can do. We're mostly giving them notes, pentatonic scale, again, that are going to sound pretty good with each other. On the other hand, this is what you do with human musicians, right? You're not, your husband didn't build the cello. On the other hand, the cello can play any note, but a piano can't play every note. You can only play the notes you have. So harmonica can only play the notes you have. That's not actually true, but generally that's true. So these questions become a little complicated to answer in a clear way, but I would say clearly the mahout is not telling the elephant what rhythms to play nor what notes to play. Mostly it's just stop and start.
So there wasn't a question about intent. So like playing music implies conscious intent, but it does seem like they're at least choosing at some point kind of where and what to play or hit.
Yeah, so consciousness is an issue that we can chase for much longer than our discussion can last. You know, are we conscious? Are they conscious? I think in my view, it's more Occam's razor like to say other species that why is our, if we're conscious and they're unconscious, this would require something very complex. Because like I was showing you, their auditory cortex is not different than ours. The ability to have complicated behaviors for dogs and cats that you're familiar with, or horses and sheep and cattle, pet birds, animals that we're used to, is already extraordinarily complex. It's very hard for you to get your cat to do what you tell it. But for elephants, it's much more complicated than that. And so I think to say that there's not consciousness, volition, and even things like a sense of humor, because I've experienced the elephant sense of humor. I could get into that a little bit, but they have a sense of humor. So to me, saying that it's not conscious is just like stretching it more than saying they're automatons. To me, they're not automatons. They have individual personalities. Some elephants literally are babysitting the mahout's babies. Other elephants will kill you if they get a chance. There's an enormous breadth of personality between elephants and within an elephant. Some of the sweetest elephants can also be killers. So, and I'm afraid I've never seen an elephant kill anybody, but I have seen elephants attack somebody. And elephant, believe me, you have, you know, it's very frightening. So, and I've also seen them to be the sweetest, sweeter than us, if I may say that. It would be like your best friend ever. So there's just an enormous breadth, and to say that's not consciousness would, you know, I can't really fathom it, to tell the truth. On the other hand, proving that is going to need a good proof, and that's not easy to come up with.
All right, Dan asks if you can speak to how musicians can look at a score and hear the music, or how a conductor can read the score and know what it will sound like. What are their brains doing in that case?
That's a good question. A lot of it is just familiarity with what we were talking about, the intervals of the frequencies. So when you do this enough, you start to look at a row of, in this case, notes, which is what he's asking about on the score. And you go, aha, I know what that sound is. So that's a big part of it. And then, of course, rhythm. Even if you have a hard time learning the notes, because it becomes a little harder as we get older, anybody can learn the rhythm. You can learn what a half note is and a quarter note in a musical score, and you can count it off, and then you can read the score. At least you can read the rhythm. And if you practice with the piano enough, you will be able to do it as well. I mean, I can do it, but I can't. But If scores get complicated for me, then I can't do it. And then I have to sit at a piano and work it out or whatever. A very, very good conductor, a very good conductor can usually do most of it in their head, but that's because they've gone through so many scores and they've seen it all and they have an idea. And even they will be tripped up over and over and over again because it won't sound the way that they think it's going to sound.
So there's a question that I thought was interesting is there a scientifically established therapeutic usage of music for patients?
So that's a tough one. I'm going to say yes. For one, Parkinson's disease patients in particular can be improved by music and dance. And, you know, our culture may look at music and dance as two separate things, but other cultures do not. And even frankly, even our culture doesn't. We just kind of pretend they're different. So it's been very therapeutic for them. Now, there's a lot of people working on music therapy, a lot for learning disorders, a lot to relax people. And one that's quite controversial, but may end up being useful, but I'm not guaranteeing it, was advocated by my late friend Gordon Shaw, who wrote the book, The Mozart Effect. And he thought, not only does learning music make kids smarter, so he advocated teaching everybody as a youngster to play, in this case, the piano. But I don't see why it has to be the piano, but whatever. But learning to play an instrument, he thinks that this helps kids learn things that have nothing to do with music, and he may be right. And then it may also help treat epilepsy. And so there is a body of research that's pretty controversial, meaning they don't agree with each other on how effective music can be, particularly for childhood epilepsy. So I'm not going to rule it out that at some point it may be that kids with seizures may be able to put on headphones with music and get a therapeutic benefit from it. So, so I'm going to say, yes, some things quite well demonstrated, other things potential, not well demonstrated, and potentially a lot to learn. But it is quite striking that Parkinson's patients who have difficulty in initiating movement can initiate movement with music often perfectly.
So there's a very specific question here. Stephen Chan asks, if middle C is 256 hertz, 2 to the 8th power, is that an accident?
That's a great question. Yes, I believe it's a complete accident. The fact that it happened that way, I think middle C has a very interesting history. So if you go to an old church keyboard, like the one, if you go to the Pantheon in Rome, you're going to see a little church, the Pantheon is way old, right? Keyboards only were established, what we think of keyboards, were only established in Middle Ages, Renaissance in Italy. And they're 4 octaves, and the middle note is middle C, okay? Now, but the thing is, at the time, all the music, so all the plain song and motets and so on, I'm losing everybody who's not a musician, so I'll try to say this quickly, could only run from the low G up to the C, 2 notes above middle C. The low G was called gamma for G. The high C was called ut, because instead of do, re, mi, originally it was ut, re, mi, fa, sol, okay? And la, ut, re, mi, fa, sol, la. Okay, that was the old scale. And later it became called do for acute reason, but the Italians at the time called ut. So when we say the whole gamut, that is gamma to ut, meaning that's all the notes you had to play. But the thing was that those are the notes you had, but you could move them anywhere. And in fact, in Indian classical music, you still do that. So the Indian classical music has, in principle, 24 notes. 24? I think it's 24. Anyway, the notes they learn to sing, depending upon the mode or raga, sa, re, ga, ma, pa, da, ni, sa. The sa can be anywhere. All you have to do is retune the do, the do or the sa, and the drone instrument, which this is getting so nerdy. In the Hindustan, it's the tambura, that instrument, or in the South, it's usually harmonium. And you can tune that anywhere. You can tune it anywhere you want. You tune it to where the singer or the instrumentalist is comfortable. And in Renaissance music, it was the same thing. So that this just ended up becoming C after a few hundred years of C being anywhere you wanted. I believe, Steve, that is it's just a funny coincidence, in my opinion.
Well, I don't think you're losing anybody, because we still have a ton of people, and lots of people are putting in questions faster than we can get to them. So there's a couple questions here I'm going to combine. Somebody says, why can some people not sing in tune? And somebody else asked about perfect pitch in a musician. So kind of how do we get those?
Very similar questions. So these are a little bit mysterious. They're being studied a lot at, I mentioned, Montreal Neurological Institute. So if you're into it, go to PubMed, which is free, and look for papers by Isabelle Peretz, P-E-R-E-T-Z, I believe. And she writes quite a bit about this. And also there's some other people out there, a fellow named Robert Zatori, and they've been working quite a bit on trying to understand this. It might be that perfect pitch happens when the connections between the different parts of the cortex are stronger. Now that is a vast oversimplification, but under some conditions, they will play a note for somebody that's perfect pitch, and the other side of the brain from the auditory cortex that's perceiving it will be strong. Now, what does that mean? It's possible that almost all of us have perfect pitch, but if you didn't grow up very young in a musical environment, you didn't learn that note was a C sharp. And later you can't establish that. And one simple demonstration of that is usually when you learn a song very well and somebody says sing it, you will usually, but not always, sing it in the same key that you learned it in. Now you don't, quote, have perfect pitch, but obviously you do, if you do that. So that's, I understand, there's a lot of critiques on that, but that is a suggestion. The thing about what Isabelle Peretz calls amusia, which the rest of us call tone deaf or out of pitch, that's also been a bit of a puzzle. Now, there are injuries that brain injuries people can get in the cortex. And particularly around the auditory cortex, I'm pointing here because that's about where it is, where people that formerly could sing in tune lose the ability to do so. So it could be cortical, but of course it could be the ear as well. And sadly, there's some singers like Tony Bennett, who's in his 90s and still sings beautifully in tune. And there are other great singers who I'm not going to name because why, who are great singers, but then start to lose their pitch. And we know this. Some of that can be cortical, but some of that can actually be literally loss of some of the cells in the cochlea of the ear. And they no longer can focus in the auditory pathway on exactly what pitch that is. Now, for people that don't have an injury and are out of tune, and certainly I know them, including professional musicians. I have a friend who, again, I'm not going to name, who's one of the top people on a particular orchestral instrument, and I mean one of the top, and this person cannot sing in tune. And you go, how's that possible? And I can tell you it happens. So where's that happening? Is it an inability to hear oneself? Is it an inability to control the vocal cords? Is it something funny in the wiring of the cortex? Any of these are possible, and they're probably multiple reasons. A related question would be, why do people get tinnitus, sounds in the ear, particularly as they get older? And there's about 12 different answers to that question. And they can be problems in the ear, problems in the cortex, problems in the auditory nerve, problems in bones in the ear. And so there are multiple different causes of this sort of thing. So yeah, auditory pathways can start to get pretty complicated.
On the same thought, Janet asks if you could talk about why certain sounds get more irritating as you get older. So her 92-year-old mother can no longer stand the sound of a really nice violin, but she loves the timpani and the cello. So is that kind of the similar thing as you age, they just change?
Yeah, and also there might be damage to the sensory cells of the ear, which are called hair cells, although they don't have hair. They have little microscopic tufts that look like hair, which is why Corti, or whoever the Italian anatomist was who started, Cortese, I think, who first described these, called them hair cells, and we continue to call them that. Now there are different classes. There's so-called inner hair cells, which are very well tuned to different pitches. So if you lose those, you won't be able to tell the pitch. But there's another class of hair cells called outer hair cells that act as amplifiers. Because you can think about it, the change in air pressure that we're hearing is actually very tiny. Because when I'm speaking, I'm not really changing air pressure very much, right? It's not like, which just changed a lot of air pressure. So the outer hair cells act like amplifiers to make the very small changes in air pressure louder. And we can hear over 1 million-fold differences in air pressure and volume. But if these outer hair cells get damaged, and this can happen through aging, but it can also happen through, I'm afraid, smoking, some kinds of drugs, and it particularly happens with loud noise, including loud music. And as those get damaged or die, then the ear has less ability to sort of adapt itself to the volume of what you're hearing around you. So something that's very quiet, someone with outer hair cell loss will not be able to hear, and then there's this little band where they can hear well, and then it becomes loud, and then the outer hair cells are going nuts and shaking the cochlea like crazy, and that becomes painful. So that is my best guess for the questioner's 92-year-old mother.
Great. Well, we are basically at the end of time here, and we have like a dozen or so more questions that we didn't get to. So thank you everyone for tuning in, staying with us this whole time. We did record this. It will be posted on our YouTube channel in a couple days. I will send the link around, but Professor, do you have any closing thoughts for us?
Well, thanks to you, and go Lions. Whenever the Lions come back, I hope they go. And other than that, I appreciate everybody's when you do this kind of work or write about it, it's really satisfying as a writer in this case, or a musician, to know that people are interested in it. And so I really thank all you and everybody in the audience.
Absolutely. We've gotten just a dozen comments already coming in saying thank you so much. It was so interesting, really fascinating. So thank you again, and everybody have a great night.
Thanks. Bye now.